For the second session today, we have Paolo Perotta. Is that fair? Is that a good pronunciation, or was that a terrible? Perfect. Everyone get that? Perfect pronunciation. He's a well-known author in the Ruby community. You might have read some of his books. I'm sure he'll tell you about them. He currently resides in Bologna. My Italian is obviously terrible. That is the seventh largest city by population in Italy. Did you know that? It is. It is also where Ducati, Maserati, and Lamborghini are all based. And I presume you have one of each? Is that
I don't really use them much these days. But yeah.
And you're here to talk about machine learning?
Correct.
Okay, good. We do have John Connor on speed dial, just in case anything goes wrong during the talk.
Cool.
But,
Thank you, mate. Thank you.
Take it away.
Thank you. Thanks. That was a very flattering introduction, which is not surprising since I wrote it myself. So, talking about machine learning, which is kind of a frustrating topic for me for a few reasons. First, of course, because I can't understand, or I couldn't understand how it could possibly work. It's like crazy. I mean, I've been doing software for a very long time. You would imagine I know this stuff, but how can a computer, caption pictures? Or that sounds like magic. And then I got around to study it, and that was even more frustrating, because it's not that there isn't enough documentation online. In fact, there is a boatload of documentation, but it's just not targeted at me. It's for different people. It's for researchers, mathematicians. So you want to learn something, everybody's like, sure, read this paper. It has everything that you need. I don't want to read the paper. I don't want to, sift through all those formulae. Can't you have a blog post? So I hope to save this frustration for you, at least in part. This is machine learning explained to humans. And by humans, of course, I mean developers. And disclaimer, this is going to be basic. If you know anything about machine learning already, then this is probably not for you. On the other hand, if you wonder how the magic can happen, this is a talk. I hope that I will demystify machine learning. Okay, I cannot teach you machine learning in 40 minutes, but maybe I can remove some of the magic from there. So there is going to be some mathematics. There is no way around that. I will try to make it intuitive. Okay, so let's start with a simple example. Let's say that we have a small restaurant, okay, a pizzeria. And every day at noon, we get a certain number of reservations. Let's call that number X. And every night, we sell a certain number of pizzas, which I would call Y, okay? And what we want to do is to build a software program that can learn the relation between reservations and pizzas. And then we want to use that program to forecast how many pizzas we are going to sell tonight based on the reservations. For example, to prepare enough dough, okay? This is the idea. So this program has to learn from something. So let's start by collecting examples, by looking at what happens, and maybe we list all these examples in a text file. And there are these two columns there, reservations and pizzas, X and Y. The first column is our input data, and the second column is what we are trying to forecast. And machine learning people have a weird name for these variable that we're trying to forecast. They call it the label. It's like somebody labeled each piece of input data with the matching number of pizzas, okay? Weird name, bear with me, okay? First thing, we need to import these data so that we can use in our code. So I will use Python for that, sorry. I'm a certified Ruby fanboy, but this is machine learning, okay? And everybody's using Python. So I don't want to go against the flow here. I try to use Ruby, but then I was missing the libraries. So it's OK to be multilingual. And in this case, we have this nice library called the NumPy, which is a numerical library that is just fine for this. So you don't necessarily need to understand in detail what load text does. It loads this file into two arrays, x and y. And this is what we need. Okay? Now, the assumption we have is that there is some relation between x and y. Otherwise, this is all for nothing, right? And this relation is not an if one. It's not one reservation, one pizza. Some people don't reserve. Some people don't eat pizzas. So we need to understand that relation, and it's hard to understand it by just looking at numbers. We should plot it, and then we can actually see what it looks like. So reservations, pizzas. And if we plot it, that's what we get, a few dozen examples. And now the relation is jumping at us. Now we can see that indeed, more reservations generally mean more pizzas sold. How can we move from here to a program that can forecast the future? There is a way to do that, and it's pretty old. Statisticians have been using it for a pretty long time. And it works like this. It works in two phases. Phase one is trace a line that pretty much follows those points. Phase two is forget about the points entirely, just to use the line. So essentially what we did is we approximated the points with the line, okay? We simplified our data. And now that we have this line, we can use the line to make a forecast, to infer the number of pizzas. For example, let's say that we have 25 reservations today. How many pizzas do we expect to sell tonight? We can trace all the way up to the line, and then all the way left until we cross the pizzas axis. And that place where we cross it, that's our answer, okay? And the answer in this case is 42. Of course, it's a coincidence. OK, so maybe you heard about this. It's called the linear regression. That's the name. Because linear, because we're using a line, as opposed to, I don't know, some complicated curve. Okay? And regression is statisticians speak to say infer the value of a variable from another variable, like pizzas from reservations. So let me repeat how linear regression works. This is going to be a bit of a refrain today. Approximate the data with the line, and then use that line to infer the value of data that you don't have a label for, reservations without pizzas. Now, we need to put this in a form that we can actually write code on. A slightly more formal form, not a graphical form like I did so far. So how do we do this? Let's start with the second step, actually, because it's easier. Then we will go into the first step. But let's assume that we have a line. How can we infer the number of pizzas in a way that we can put in code? So first, we need to formalize this line a little bit, somehow, okay? And to do that, we have an equation like this. It's a relation between x and y by way of those two parameters. You might have studied this formula, maybe in a high school. It's just the equation of a line. Maybe you call the parameters, I don't know, a and b. I'm going to move around a lot. If I fall, I would like the entire room to fail to acknowledge this event, okay? So let's all feign indifference together. So this is the equation, okay? And the parameters are called W and B, which stands for weight and bias. More weird machine learning names, sorry, okay? Intuitively, the weight is the slope of the line, okay? You can see that for the same x, if we have a bigger W, then we get a bigger y, all right? So it's like the line is becoming more vertical. And B is that distance, the place at which this line crosses the vertical axis, the y-intercept, if you wish, the bias, okay? So now that we have this equation, we can write code about it. because, for example, let's say we have 25 reservations, so x is 25. And if I tell you that for this particular line, we have a w equals 1.2 and b equals 12, which looks about right, we can just replace this stuff in the formula, and there you have it, 42. And the code that does this is just a one-liner. I can write a function called infer that takes our input data and the line. Remember, those two parameters are the line. They identify the line uniquely. And it returns the formula. And that's it, OK? One little detail, I called this y in the very beginning, but then I changed it a little subtly, and I started calling it y hat. I put a little hat on top of the y. The reason for that is that I already used the letter y to mean the label, and this is subtly different. This is not the label. The label is the ground truth. It's the number of pizzas we actually sold. This is the inference of the pizzas we expect to sell. So I wanted to avoid any cause for confusion there, OK? So we have this infer method, and this is the second step in linear regression. It's done. That's all it takes, OK? Now, the first step is trickier. So I will ask you all to hold on for 10 minutes. That's how long it takes. But it's important. It's crucial to the entire process. So how can we go from these points to a line, to a W and B? Let's start by observing that whatever line we can trace, it's going to be wrong, right? I mean, unless the points are exactly aligned, which is not going to happen, any line has an error. Just to prove my point, here, let's look at our original data again. Let's pick one of these points, like that one, 14, 32. We're talking about that point here. 14, 32, cool. But that's not what the line would say. The line that we traced would say, OK, this is 1.2 by 14 plus 28.8. So it's wrong. There is an error. I will mark this error in orange, that little space there. So now let's write a function that considers all the errors together. Let's call it the loss, yet another weird machine learning name. Every time you hear loss, your brain should say error. That's what it is. And it takes our examples, together with the labels, and the line. And what it does is, first, it calculates all the errors. Okay? So it uses infer to calculate y hat, and then it calculates the difference from y. Notice that now the errors are an array. All these things are arrays. And that's the reason why I use in NumPy, because it makes operations on arrays very seamless. OK, now these errors, some of these are positive, some of these are negative, which doesn't make much sense at all. I mean, we don't, that depends on whether the points are above the line or below the line, right? So it might be negative. And we don't want that to happen, because we don't want positive and negative errors to cancel each other out. So let's make them all positive, which traditionally is done by squaring them. The double star operator in Python is the power operator. And now we can just average them. So this is the formula that we can use for the loss. There are other ways to compute a loss, but this is a very traditional one. It's called the mean squared error, because that's what it is. It's the mean of the squared errors, OK? Why did I take you on this merry detour? Remember where we started from. We wanted to find the line that best approximates the points. Instead, I built a function that gives us the error of the line. That's because now we can reframe the problem like this. We want to find the values of the parameters that give us the minimum value for this function. Right? And this function looks like it has 4 parameters. But if you think about it, x and y are not really parameters. They are constants. Once we have our examples, those are done forever. So the parameters are actually W and B. That's the line, okay? How do we find the W and B that give us the minimum value for the loss? Hold on another few minutes. This is going to take some math. First, let's plot it, because if I don't see things on a chart, then I have trouble wrapping my head around it. What does the loss look like as W and B change? I tried plotting it, and here it is. Beautiful little surface, okay? I spent like half an hour finding the exact color scheme. And that's the weight, that's the bias, and that's the loss. And where we want to be is here, the minimum, okay? We want to find that place, those values of weight and bias. That's the line. How do we do that? There is a beautiful little algorithm that is arguably the most fundamental algorithm in machine learning. And it works like this. First, start wherever. Any point will do, okay? I'm starting at that white spot there. And then use this mathematical tool that is called the gradient. For those who don't know, the gradient is essentially the slope of this surface. The more sloped, the bigger the gradient. And it's pointing in the direction of the maximum slope. Let's be concrete. First of all, we can calculate the gradients for W and B separately, which is a little bit like slicing the surface like this. So I'm first fixing W and varying B, the bias, and this means that I'm essentially slicing the surface like this, okay? It's like slicing it with a katana like this. It doesn't have to be a katana. I mean, a katana just makes it sound cooler, okay? And then I'm doing the same thing in the other direction, okay? And then I can calculate the biases with mathematical formula, which is akin to saying, okay, there are two arrows there pointing uphill. The more sloped these curves, the bigger the arrows. Again, I'm sorry for people who are into math. Please go easy on me. I'm trying to make this intuitive, the way I understand it, okay? Now that we have these, we want to go downhill, okay? And conventionally, the gradient points uphill. So let's revert them. And another thing that we want to do is to multiply them by some factor to make them smaller, by some constant factor. Why? Because we don't want our steps to be too big. We don't want to overshoot the minimum and maybe find ourselves even farther away from it than we started from. Okay? And now that we have these, we can just add these amounts to W and B, which means that we move. And then we do it again, okay? And again and again. It's iterative. And we keep doing it until we reach the precision that we want to reach. So like a ball rolling over this surface, we will roll down the gradient until we reach the minimum, or we get close enough. This algorithm is called the gradient descent. Doesn't sound like much, but it's essentially, it's fundamental to all the artificial intelligence that you see around that does amazing things. It's a beautiful little thing because it's self-correcting. For example, we might actually overstep the minimum, but then the gradient just reverses, right? And as we get closer and closer to the minimum, we are taking smaller and smaller steps. So actually, we get more precise because as we get closer, the surface flattens. The gradient gets smaller until eventually, at the minimum, the gradient is 0 because the surface is exactly horizontal. Okay? So now, formula. I don't know whether you're comfortable with this. If you are not, you can safely ignore the math. You know what's uncomfortable? I left my gear out in the sun here in Sydney, and now this presenter is sticky. I can't tell you how gross this feels. If if you are feeling uncomfortable with this, think about me in front of 400 people holding a sticky presenter. So this is just the loss. I'm putting it here in mathematical form for those of you who like to see the formal shape of it. It's, you know, this is wx plus b, which is y hat minus y, the error, squared. That's a sum sign, and then we divide by the number of examples, which I call them. So it's mean squared error. And I'm putting it here only because some of you who know calculus might actually be able to calculate the gradients in your mind, possibly. It's, you probably remember this stuff under the name partial derivatives. That's what they were for. So yeah, these are them, the gradients with respect to W and B. But if you don't know how to calculate these, I can only tell you it's not rocket science, but we always have textbooks to resort to. So you don't have to calculate them, actually. So we already have the code for the loss. Here it is again. I just inlined a variable to make it a one-liner, but it's the same code that we saw before. And now we can write another method to calculate the two gradients, both of them, and we return both of them. And now we're almost done. We just need one more piece of this puzzle, which is the method that actually does the gradient descent. It uses these methods to step closer and closer to the minimum. And here it is, okay? I called it find best line. And it's taking the examples, plus a couple of parameters, which I will describe in a minute. It starts by giving any value to W and B. In this case, it's 0 for both. And then it gets into a loop. And in this loop, first, it prints out the loss so that we can visually inspect it and check that it's indeed decreasing at each iteration, okay? Otherwise, there is a bug somewhere. We want to get closer and closer to the minimum. And then it calculates the gradients. It multiplies them by alpha, the factor, the constant factor I mentioned to make it smaller, so that we don't end up too far from the minimum. And then it's reverting them and adding them to W and B. And it's doing these iterations number of times. So that we need more precision, we just raise the number of iterations. It's as simple as that, okay? In this case, we actually don't need much precision at all. We are computing pizzas, not, you know, computing the size of electrons. But okay, it's just as an example, we can iterate for a while until we reach a certain precision. And then it returns W and B. It returns the line. So this finds the line, okay? And we can actually see this thing in action. I have code here. Okay, sorry. So let me show you the full code first, which is exactly what we saw so far. It's nothing new, but I'm making these quite large because from these lines, maybe you have trouble seeing there. No, you don't. So it's me having bad eyesight. Okay. Thank you, mates. Okay, so you know the infer method. And the loss gradient and find best line methods, we just described them. Okay? And then there is some main code. It loads the data into two arrays. Then it uses that data to find the best line, to find W and B, with quite a few iterations and an arbitrary alpha multiplication factor. I actually tried multiple values there, and I ended up with a value that looked like it worked fine. And after this, it prints out the parameters it finds, so we can take a look at them. And then it goes into the second phase of linear regression. It makes an inference. It says we have 25 reservations. What's y hat? What's the number of pizzas for these? And it prints out the result. Okay? And then there is some additional plotting code to show the data and draw the line so we can check visually that the line is indeed approximating the data. Okay, does it make sense? It's not much code. I mean, apart from the plotting code, it's actually quite short. And I'm also splurging on the white lines. Okay? So, okay, if we start it, okay, you can see visually that the loss is decreasing at each iteration. Okay? And this looks like a fine line to me. And at the end of it, it found these parameters for the line. And for 25 reservations, it's telling us, okay, so you can expect to sell 40.23 pizzas. That's the thing. That's linear regression in action. So now we have both phases of linear regression in code. And now, believe it or not, you know how machine learning works. Toy example? Yes. But not quite. Let's generalize these a little bit. First step, you have data, you approximate the data, in this case with a line. This is a phase called training in machine learning, for obvious reasons. Here, computer, here are a few examples of the real world. Learn. So the computer is training on the examples by finding a shape that fits the examples. In our case, we decided that the shape would be a simple line. What if we want to do something really complicated? What if we want to recognize cat pictures? That's always the example about machine learning. Recognizing cat pictures is the thing. Okay? Well, then maybe we don't have a few dozen examples that are tiny. Maybe we have a few terabytes of images. Okay, still the same idea. That's data, right? We want to find a shape that approximates the function that underlies that data. Maybe it's not going to be a line. Maybe it's going to be a mind-blowingly complicated curve in multidimensional space. Still gradient descent. More sophisticated gradient descent than my Python 4-liner? Yeah, sure. Still gradient descent. We're still moving along that very complex, mind-boggling, Cthulhu-like curve in space, trying to minimize parameters. How many parameters? It's not going to be 2. It might be a few millions. Same thing, in any case. Still descending the gradient with respect to those parameters. And then we use the line to infer and label data, the line or whatever shape we have. We use those parameters to try and come up with a label for stuff that doesn't yet have a label. Is this a cat picture? So these two phases, there is an analogy you can make actually with coding in that training is a little bit like compilation because it's expensive. Conceptually, it's a very vague analogy, but bear with me. It's expensive, right? We actually spent, a few seconds to run a very simple linear regression on this computer. And just imagine if you have a few petabytes of images and you want to do a regression, some form of complex regression on them. Of course, you're not going to use linear regression. You are probably going to use more sophisticated algorithms which have multiple layers of a regression, many layers of regression maybe, and that's what's called the deep learning today. It's very fashionable. But it's the same idea. It's just very expensive. Maybe it doesn't require my computer. Maybe it requires a rack of GPUs and days or weeks of training. That's why machine learning is taking off now. because we have the hardware, all those GPUs, right? That's when we don't use them to mine Bitcoins. And we have the data, or at least Google does. I don't, but they do, and Facebook. So we can actually do very sophisticated training. Inference, that's cheap. For us, inference was like X multiplied by W plus B. Okay, if you have many, many parameters, that might be a more complicated formula, but it's still about just replacing parameters in a formula. That's why your cell phone can recognize your face. Training that software to recognize faces might have taken a huge amount of computational effort, but once it's done, a cell phone is more than enough. Smartphone. So that is the thing with machine learning. Now, at this point, I wish I had the entire day, and believe me, I tried. Because you might still have a nagging doubt, like, okay, this is nice, linear regression, okay, you can compute pizzas, but it sure seems like quite a jump towards computer vision, for example. So I can tell you there is a path up to that, but you might go like, okay, but I promise, if I had 2 hours, I could actually show you step by step how to move from here up to computer vision, and you would understand every single line of code in the result. I cannot do that. But the thing is, I convinced Nick and Mel with some, mild Italian-style threats to give me an extra 20 minutes tomorrow. And what I can do is I cannot take every step like I did today, but I can give you a very quick, here, I drew a map, actually, and a very quick 10 miles high view of the road that you've got to take from linear regression there to the fabled land of computer visions. And okay, it's not going to be very detailed, but I'm going to try at least, and to give you a broad idea of how it works. So I'm going to end this on a huge cliffhanger, and and for now, thank you. I'm done for the day. Okay.